Today, we want to look at definite integrals some more, just to review what we looked at yesterday, build things up to the Riemann sum, and how that leads to the definite integral, and the important differences in the two, and why this is such an important equation that we've written up here. Remember, we want to calculate a definite integral, and y'all trusted me when I said the definite integral will tell us the area under a curve and above an interval. And the big idea is that we're trying to calculate an area. And all we need for area is length times width. And that shows, so area is equal to length times width. And that's our basic formula that we're using here. Area is length. I spelled length wrong. Length times width, since I apparently am going to have trouble spelling today. So area is equal to length times width. Now, when the length is constant, we get to multiply. When length is constant, we get to multiply. When the length is not constant, that's when we have to make the length constant. We have to go from multiplication to addition. This is useful because multiplication is just repeated addition. If everything is the same in our addition problem, then we get to use multiplication. That's the core thinking that's going on here. So when length is constant, we get to multiply. If length is constant, then we get to multiply. But if all of our terms are not the same, then we are stuck with addition. We have to keep it at addition. So if length is changing, then we have to drop back to addition. Multiplication is the fast addition, but we're going to need the slow addition because not everything is the same. So the length times the width shows up right here in this f at xi times delta x. Here is length times width. And so we're adding up the areas of a bunch of rectangles. So this next piece says add up the areas of n rectangles. And then calculus steps in the room and said, hey, don't forget about infinity. And then this last piece, the Riemann's part, last part of the Riemann sum is more rectangles means more accuracy. So use infinitely many rectangles. More rectangles gets us closer to exact area. So use as many rectangles as possible. And that's the calculus way. If doing something more often gets you closer to where you want to be, then do that thing infinitely many times. Then the other things that we're thinking about is that, oh, I already mentioned that. Multiplication is our fast addition, but only works when everything is the same. So what we have here is when infinity comes into our, we have an infinite number of rectangles, we switch over from a discrete sum where we have a countable set of rectangles. We can number them 1 through n. And now we're finding a continuous sum. So here are the two ways that we want to think about integration. Integration is multiplication, where one of the factors is variable. That's number one. Integration is multiplication . but one of the factors is variable. Integration is multiplication, but one of the factors is variable. We also want to think about integration as addition, but not a discrete sum. We want to think of it as a continuous sum. Integration is a continuous sum. It's a continuous sum, and this is rather than a discrete sum. Rather than a discrete sum where we can write down each of the different terms, x1 plus x2 plus x3, and so on. We actually study these infinite sums in a different form when we are looking at sequences, series, and power series later. So in integration, the terms are getting infinitely small. So that's, and we're stacking an infinite number together. So these rectangles are getting infinitely thin. But in sequences, series, and power series, we start looking at discrete sums that go on forever. So we're going to come at these infinite sums in a couple of different ways. We'll talk about infinite discrete sums and these continuous sums. Continuous sums being integrals, definite integrals in particular, and infinite discrete sums being series. So there's more that goes along with this. In addition to the thinking that goes behind definite integrals. So this is all the definite integral thinking and how we build up to the definite integral. This is, on one hand, super practical because we're just thinking about calculating a definite integral by calculating an area. And on the other hand, it's not quite as practical because if we have a function, what if there's some other way to calculate our definite integral? Going back to the previous one, it's super useful because if we think of integration as multiplication, but one of the factors is variable, we now have a key to figure out when we can use integration. So here we're using as a basis area is equal to length times width. What we saw in chapter 5 was how do we measure distance traveled? We're using a multiplication again. Distance equal to rate times time. If the rate is constant over the entire time, we get to multiply. So think about other applications. So another example of a multiplication is that distance is equal to rate times time. Distance is rate times time. If the rate is constant over the entire time, then we get to multiply. If rate is constant, then we get to multiply. If rate is constant, then we get to multiply. So if we drive at 60 miles per hour for 8 hours, we get to multiply those two to find the distance. 6 times 8 is 48, so 480 miles. No problem. Distance is equal to rate times time. But if the rate is varying over time, if the rate varies over time, if the rate varies over time, then we'll have to integrate. We'll have to calculate the rates at a bunch of different times. Assume that it's constant for small pieces of time, delta t's, and then calculate with multiplication, because that's what we're trying to do when we break things up into little pieces. Then we get to multiply rate times that little piece of time. Then we go on to the next piece of time, calculate the rate there, multiply by the time, and then add up all those distances. And what we're doing is we're integrating the rate with respect to the time. So then, we integrate the rate with respect to time. So if the rate varies over time, then we'll integrate the rate with respect to time. So in that sense, we are integrating from A to B the rate with respect to time. This is a fairly lazy yet descriptive notation of what's going on. Integrate the rate with respect to time. Oops. I wiped out my writing. There we go. Got to remember, this takes longer to dry. Any questions?
Can we do one of the homework problems?
Which homework problem?
Any is fine.
No, I don't do any problem.
Okay, how about question 1 from 5.01?
Question 1 from 5.01. Let's take a look at that problem and see what we got. Okay, so in this problem, we've got a bunch of information, and we are going to be forced to assume that the rate is constant over time, because we don't have continuous information about the rate. So let's switch pages. Let's take a look at the information that we're given in this problem. Let me center my board. So let's take a look at the information we're given. We got time since brakes applied, so time. Chapter 5, section 1, problem 1. So we've got time measured in seconds, and we've got velocity in feet per second. How old school of us. At 0 seconds, when we hit the brakes, we were traveling at 83 feet per second. 2 seconds later, we are traveling 45 feet per second. After 4 seconds, we are traveling 14 feet per second. And we finally came to a stop at 6 seconds. All right. So in this first 2 seconds, if we assume that we are traveling at a constant velocity, we have an over and under estimate. So for the first 2 seconds, we can assume that we are traveling 83 feet per second or 45 feet per second. This is just one technique. So we say, well, we started off this period of time going 83 feet per second. Let's just use that for that first 2 seconds. So if in the first 2 seconds we were going 83 feet per second, that means we went 166 feet. and that would be an overestimate. Or we could say that we're traveling 45 feet per second for that whole first 2 seconds. We hit the brakes at 0 seconds, immediately our speed dropped down from 83 to 45, and we just did that. In any case, that would be an underestimate or a lower bound on the distance that we traveled. So that would be 90 feet in the first 2 seconds. So now we have a lower bound and an upper bound on the distance that we traveled in those first 2 seconds. So here's a lower bound. Oops, no, that's the one that I want. Here's a lower bound. And here's our upper bound. In those first 2 seconds, we traveled somewhere between 90 feet and 166 feet. That's a terrible estimate, especially when we're talking about a car coming to a stop. You don't want 166 feet is pretty long way to go, especially we weren't traveling that fast in the beginning. Now we just have to do this for the other 2 rectangles. So we can look at this and we can see, we look at this. There's the first 2 seconds. And we're going to think of 3 rectangles. We're going to think of 3 rectangles with a delta t of 2. So now we have an upper and lower bound for the first 2 seconds. We could just go for the other 2 rectangles. Any questions? In question 4, we're looking at a graph. So let's scroll. And I don't think they're putting zeros in front of the 4s. No, that's it. This rest of the semester is canceled. I messed it all up. Just kidding. I'm not going to get out of this that easily. So in question 4, we essentially have the same information. We've pretty much got the same information. We have a graph of our velocity starting from home. In this case, we have a couple of changes. We have positive velocities taking us away from home and negative velocities taking us towards home. And then consider A equals 2 and B equals 25. So if we look at, try to replicate our picture here. If we look at time t equals 0, so this is t in hours. And here we have our velocity in kilometers per hour. What we're going to get in question 4 is pretty much the same type of information that we had in question 1. It's just showing up as a graph rather than as a table. So at time t equals 0, it looks like our velocity was, let's see, 1, 2, 3, and B is 25, so 75 kilometers per hour. So it looks like it starts off at 75 kilometers per hour. And then it travels up to, so A is 2. It looks like at 2, we were close to 100. So it went up a little bit. I'm going to mark that point as 2 and 100. Well, I'm also going to summarize over here, or down here maybe. And then at 4 hours, it looks like we are back down to 75. Then at 6 hours, we go all the way down to 0. Oh, we hit traffic. And then at 8 hours, looks like about halfway, but at 10 hours, we're down to -25. So 8 hours, hard to say. And then at 10 hours, we're at -25. So if we read the graph, and just write down the information that we have, we can use this to approximate our distance traveled. So the first part of the problem asks us to approximate where were you at the end of 10 hours. What we want to observe is that in this first half, for 6 hours, we're traveling away from home. So in these first 6 hours, try to replicate this graph up in here. So the graph is doing some stuff. Not exactly this, but for those first 6 hours, we're traveling away from home. So I'm going to call this area A1. And we're going to notice for the first 6 hours, we're traveling away from home. And we've gone a distance of A kilometers, or A1 kilometers. Our derivative, if velocity is derivative of our position, our derivative is positive. And so our distance is increasing, and the area tells us by how much it increases. We'll get to figure out how much that is in a second. And then from 6 to 10 hours, from 6 to 10 hours, we're traveling towards home, and whatever the area is down here, I'll call that A2. For 6 to 10 hours, we're traveling back towards home. A distance of whatever the area is. So that'll be a distance of whatever that area is. So based on this, we could figure out we know that at one of the parts of the question is, when are we farthest from home? And that happens at 6 hours. That's when if we think back towards Calc 1 days, this is when the derivative is equal to 0, and that's when we have a potential local maximum. So the other questions are, how far are we from home at that time? So that's just A1. We are furthest from home at 6 hours, and we are A1 kilometers from home at that time. At the end of 10 hours, we've gone A1 kilometers away from home, but A2 kilometers back towards home. So we are furthest from home at 6 hours. We're farthest from home at 6 hours. At that time, we are A1 kilometers from home. After 10 hours, at this point we turned around. At the end of 10 hours, we've gone A1 away, A1 kilometers away, but we're coming back A2 kilometers. So if we subtract A2, that's how many kilometers we are from home. Now, the trick for this part is figuring out how Wiley calculated A1 and A2. And unfortunately, we're trying to communicate that to a computer. So I can't tell you what the answer is, but I can tell you that A1 Wiley thinks is 450 kilometers. I'm not exactly sure how they arrived at this. I think they did some triangle business, but I think some of their approximations go beyond what we're actually given. So the first one is A1 is 450, and then they think at the end of 10 hours, you're 325 kilometers from home. So whatever 450 minus 325 is. So they think A2 is 125. I don't want to give away the answers, but sometimes we have to, because the tolerance on the Wiley Plus is plus or minus 2%, and that's kind of impossible to hit unless you know exactly what they're doing to make the approximations. Any questions?
So would you just basically draw out the triangles and take the measurements and do all that, the calculations between the difference between A1 and A2?
Yes. So what I would do is I would look at, if I was just handed this problem, these are the approximations I would make. I would look at this first 2 hours like a trapezoid with a base of two bases of 75 and 100 and a height of 2. Then I would look at the second rectangle as another trapezoid with the bases of 100 and 75. Oh, that was the same one. And then from 4 to 6, I would just draw that as a triangle.
So you don't want us to use rectangles. You want us to get the area of two trapezoids in a triangle.
Or if you do rectangles, a trapezoid is just the average of the two rectangles. So you could do a left approximation and a right approximation, and then take the average of those two, and that'll assume things are linear.
Do we have time to do that process or no?
You just do the same thing that we did in the previous problem, length times width. In this case, I think these are variables, so my value of A was equal to 2, and my value of B was equal to 25. So we can either do left and right for the rectangles, or you could just find areas. The important thing is that we're just finding areas. So trapezoid, trapezoid, triangle, or underestimate, overestimate. The average of those two rectangles is a trapezoid. That's why the formula for the area of a trapezoid is just the average of the bases times the height.
Doesn't a trapezoid have a diagonal where the origin would start?
No, the trapezoid would be, the trapezoid would just be this shape in here. So there's base, then it would be flat there. That would be that first trapezoid. So if we have these two values, so if I have, say, two different, oh, let me make it taller there. So a trapezoid has two parallel sides and then two not parallel sides. So then there's a height. The area of a trapezoid is the average of the bases times the height. Where this formula comes from is the trapezoid is the geometric, or not the geometric, is the average of the two rectangles that contain it. So the trapezoid is the average of the two rectangles that contain it. So we think of the trapezoid as the average of the two rectangles that contain it. So here's one rectangle. I shouldn't say contain it, but so we've got this one rectangle.
It's 9 o'clock, Professor.
Okay, let me just, the small rectangle is B1 times H, and the large rectangle will be B2 times H. And if we take the average of those two things, we can factor out the H. So if we do B1 times H plus B2 times H and divide by 2. So that's where we get the area for a trapezoid. All right, so try to do that for this problem and see if you can come up with those two areas, whatever it was, area 1, 450, and area 2 of 25. And then we could figure out what Wiley was thinking, but at least you have numbers that you can drop into your, into the Wiley plus. All right, that'll do it for today. We'll talk more about definite integrals tomorrow. Everybody have a good day and thanks for playing.